All right, so remember, next Thursday is the last day to hand in any missing assignments. That's also the day of your diploma exam at 8:30 in the morning. Right? The exam scheduled to start at 9, but you want to be here early so that you can get your instructions and get everything ready to go. So when 9 a.m. comes, then you can start your exam. Right? So I put on the inside cover of that first review booklet from Transformations the makeup of the exam. That's the same as what was on that link that I put to you guys in that email that shows you the makeup of the exam. Okay, but that's there. Also, the one booklet that was missing when you guys picked up the review for, I think it was for exponents and logarithm questions, that booklet is there for you to pick up as well. Okay, so yesterday we looked at arranging objects. Today we'll do more arranging, but we'll introduce more restrictions. We'll also work with sets of objects where there will be identical objects or repetition. In many problems, restrictions are placed on the order in which objects are arranged. In this type of situation, we always deal with the restrictions first. So this first example, how many ways can all of the letters of the word oranges be arranged if first there are no constraints or no restrictions? So there are 7 letters in that word, so they could be arranged in 7 factorial ways. Right, so 7 factorial. What happened there? Try this again. There we go. 5,040. If the first letter must be the letter N, so that means you would have one choice for the first letter, and then there's 6 remaining letters that can be arranged in any way. So that would be 6 factorial. 1 times 6 factorial, or just 6 factorial. If the first letter must be an N, there's only one choice for that first position. So 6 factorial is 720. All right, question C. The vowels must be together and in that order. O first, A second, E third. They must stay together. So if one moves, the other moves with them. So to do this one, let's mark down our 7 spaces. The vowels must stay together in this order. O, A, and then E. So this just gives us one case of where those 3 vowels could be together, taking up the first 3 positions. Okay? Or they could be the second, third, and fourth, or the third, fourth, and fifth, and so on. Now, instead of doing all those different possible scenarios, here's a bit of a shortcut that we can use. Okay? And you can use this whenever items, objects must stay together. In this case, letters have to stay together in a group. What we do is we count them as one object to be arranged. If one moves, the other 2 have to move with them. They move together. So we can count them as one object to be arranged. So that would tell us in this case we have 5 things to be arranged. These 3 letters that count as one object plus the remaining 4 letters gives you a total of 5 things that need to be arranged. And so the answer to this would be 5 factorial, which I think is 120. Yep. So there's the answer to part C. Now for part D, it's similar. It says the vowels must be together, but in this case, in no particular order. So we would start it the same way we started question C, meaning that the O, the A, and the E have to stay together. They count as one object to be arranged, plus the other 4 gives us 5 factorial. However, now you have to also multiply by 3 factorial, and that 3 factorial represents the number of ways that the O, A, and E can be arranged amongst themselves. It says in no particular order, so they can be in any order. There are 3 letters there that could be arranged, and they could be arranged in 3 factorial ways. So the answer is 5 factorial, which we just calculated to be 120, times 3 factorial, which is actually 6. 3 times 2 times 1. The answer is 720. You see, this is the same thing as 6 factorial. 3 factorial is 6 times 5 factorial is the same thing as 6 factorial. So you see the difference between C and D. With C, the letters had to stay in that order. So we didn't have to worry about arranging them amongst themselves. But for question D, no particular order. So we did have to compensate or deal with the fact that those 3 letters can be arranged amongst themselves. Example 2, 5 people, Shay, Reese, Caddison, Matthew, Simone. They are seated on a bench. In how many ways can they be arranged if Matthew must be seated in the middle? So there are 5 people here. And there's only one choice for the middle person, because Matthew must be seated in the middle. There are 4 remaining people to arrange, and they can be arranged in 4 factorial ways. And 4 factorial is 24. Now part B says, what if Shay and Caddison must be seated together? So now this is similar to what we looked at above, where the vowels had to stay together. Notice it doesn't say any order. So we're going to have to deal with that as well. But first, let's mark down our 5 spaces. If Shay and Caddison have to stay together, they would count as one object to be arranged. Plus the remaining 3 people would be 4 factorial. But then we also have to multiply by 2 factorial, which is the number of ways that Shay and Caddison can be arranged amongst themselves. And there's only 2 ways. 2 factorial is 2 times 1. And those 2 ways are Shay first, Caddison second, or Caddison first and Shay second. But we have to include that to get our answer. So 4 factorial is 24 times 2 would be 48. Now, part C. What if Shay and Caddison cannot be seated together? There'll be a cat fight. Can't have that. So they got to be separated. How do we deal with that? Okay. Well, we're going to see there's 2 different ways that we can do this. I'll show you both. Solution 1. Solution 1 would be taking all possibilities minus the possibilities with Shay and Caddison together. You see, there's only 2 things that can happen here. Either they will all be together, those 2, or they will be separated. Those are the only 2 things. Right? If you take the number of ways that they can be seated together and the number of ways that they can be separated and add them together, you'll get all possible scenarios. Because nothing else can happen. Either they are both together or they're separated. Nothing else can happen. So if you add those 2 together, you'll get all possible scenarios. And so we can do this by using some reverse logic, and that is we can take all possibilities and subtract the possibilities with Shay and Caddison together. All possibilities would be 5 factorial, because there are 5 people to be arranged. And the nice thing about doing it this way is we already have our answer for the second part. The possibilities with Shay and Caddison together, we found to be 48. We did that in part B. So 5 factorial is 120. Take away the 48. Gives us 72 as our answer. So that is one way to do this type of question, where 2 things cannot be together. That's one way. Here's another way, though. So if they cannot be together, obviously they have to be separated, right? So you could have Shay in one spot, and then one of the other remaining 3 people would have to be next. And then you could have Caddison, and then one of the other remaining 3 people could be next. So these small spaces on the bottom are showing where we might have Shay or Catteson. The large spaces or large lines that I have on top, I'm going to have for the remaining other three people. Now, there's only Shay and Catteson, so they can only go in 2 spots, but we can see there are 4 places that we could choose to put the first person. Again, if these smaller lines at the bottom represent where Shay and Catteson could sit, no matter where you put them there, they're going to be separated, which is what we need. All right. So if we're looking to see where we can put, let's say, the first person, Shay, there are 4 choices to put Shay, times 3 choices to put Catteson. And it doesn't matter if you say I'm going to put Catteson first, there'd be 4 choices for Catteson and then 3 choices for Shay. So those are the different places or the number of possibilities we have to place those 2. And then we have the remaining 3 people that could be arranged in 3 factorial ways. So this should give us the same answer. 4 times 3 times 3 factorial, which is 6. So we could have just put 6 there. You get exactly the same answer. All right, so 2 different ways that we could tackle that one. Number 3, how many different 3-digit even numbers greater than 300 can you make using the digits 1, 2, 3, 4, 5, and 6, and no digit is repeated? So 3-digit number. So we mark down 3 spaces. And we're actually going to see that we're going to have to look at 2 different scenarios here. And here's why. We are told that the 3-digit number must be even and greater than 300. So there's 2 restrictions there, okay? And we have to choose from the digits 1, 2, 3, 4, 5, or 6. Now, if the number has to be an even number, that would tell us that the last digit has to be even. So we could have either a 2, a 4, or a 6 for the last digit. There would be 3 choices there. However, what if the first digit is even? Then that's going to take away the choices you have for the last digit, right? Because the other restriction is that the number itself has to be greater than 300. So the first digit could be either a 3, a 4, or a 5, or a 6. If you choose the 3 or the 5 for the first digit, then it doesn't affect the number of choices we have for the last digit. But if we choose the 4 or the 6 for the first digit, that will take away one of the choices for the last digit. So our 2 scenarios we're going to look at here is if the first digit is even, and our second scenario will be if the first digit is odd. If the first digit is just like Crummer, odd. Okay? So let's start with the first digit. Remember that the number itself has to be greater than 300. Okay? And if the first digit is even, that means it could either be a 4 or a 6. So there'd be 2 choices for that. So now let's go to the last digit, because that's where our other restriction is. The number itself, the 3-digit number itself, must be an even number. So the last digit has to be even. We've already used one of the even digits. So now instead of having 2, 4, or 6, instead of having 3 choices, now we only have 2 choices for the last digit. We've already used 1 for the first digit, which means we have 1 less to choose for the last digit. We started with 6, we've used 2, that means we'd have 4 left. So 2 times 4 is 8, times 2 is 16. The other thing is that the word or then means to add. The word or means to add, because you're going to have all the possibilities with the first digit being even, as well as all the possibilities with the first digit being odd. You'll add them together to get your total possibilities. So what if the first digit is odd? That means it can either be a 3 or a 5. 2 choices. But for the last digit, we haven't used an even digit, so now there are 3 choices for the last digit. It can either be our 2, 4, or 6. Once again, we'd have 4 choices left for the middle one. 2 times 4 is 8, times 3 is 24. We add those together and we get 40 as our answer. Okay, I mentioned yesterday we'll be talking about permutations with repeating objects. Consider the number of 4-letter arrangements possible using the letters from the word pool. So they're all written out there. There are 24 of them altogether. However, when you switch the 2 O's around, it doesn't change the way it looks. You get exactly the same word or exactly the same arrangement of letters. So there's repetition here. If all the letters were different, the number of possible 4-letter arrangements would be 4 factorial or 24. Because there are 2 identical letters, the 2 O's, which, if they were different, could be arranged in 2 factorial or 2 ways. The number of 4-letter arrangements possible when 2 of the letters are the same is 4 factorial over 2 factorial. And that'll give you your 12 answer, 12 different arrangements. So basically, again, we're just going to forget about all these bottom ones because they're the same as what's above them. So we want the number of different arrangements. We're not going to count any repeating arrangements. So this is how we deal with permutations where there are items that repeat. A set of n objects with A of one kind that are identical, B of a second kind that are identical, C of a third kind that are identical, and so on, can be arranged in n factorial over A factorial, B factorial, C factorial, etc. So in the case of the word pool, there are only 2 letters repeating, so we only have to divide by 2 factorial. But we're going to see examples where there's more than 1 letter that repeats. And so this is the method that we use to give the number of different permutations. So how many different 8-letter arrangements can you use or make using the letters of the word aardvark? So there are 8 letters there. They can be done in 8 factorial ways. But there's repetition here. There are 3 A's, so you're going to have 3 factorial on the bottom. There are also 2 R's, so you're going to have a 2 factorial on the bottom as well. When you do this in your calculator, you got to put the denominator in brackets. 8 factorial divided by, and we need to use brackets to keep the 3 and the 2 factorial both on the bottom. And 2 factorial is just 2 times 1, so I put that in there just as 2, and we get an answer of 3360. Number 5, how many different 5-digit numbers can you make by arranging all the digits of 17171? Well, there are 5 digits there. They can be arranged in 5 factorial, but again, there's repetition. There are 3 1s and 2 7s. So you divide by 3 factorial and 2 factorial, same as the previous one. So 3 factorial times 2 factorial, which is just 2, gives us an answer of 10. Switching the 1s around or the 2 7s around won't give us a different number. It looks exactly the same. Number 6, how many paths can you follow from A to B in this 4x6 grid if you may only move up and to the right? So we're going to see there's a couple different ways we can do these pathway questions. One of them is using repetition. Okay? One of them is using repetition. So basically, count the number of blocks that you have to travel. It doesn't matter what path or series of paths you follow, the total number of blocks that you have to travel is the same. So if you start at A and you don't start counting until you move, you're going to go up 1, 2, 3, 4, and then to the right, 5, 6, 7, 8, 9, 10. You're going to go a total of 10 blocks. So that can be done in 10 factorial ways. But there's repetition here, because if we look at the blocks that are going east-west, And if we highlight them with a different color, and what you have to remember is that you don't start counting until you move. Just like when I was counting the blocks, I didn't start counting until I moved. So that's why I didn't draw one of these blue lines along the bottom, because you don't start counting until you move. So really there are only 4 blocks that are going in the same direction, east and west. And so that can be done in 4 factorial ways. There's repetition there. And then the blocks that are going south to north, up and down, let's highlight those in a different color. And remember, you don't start counting until you move. So there are 6 different blocks there are different blocks, but those are going in the same direction as well. So that's your repetition. Again, you don't start counting until you move, so you're not going to highlight all of these lines. And that's why I skipped the first line in both scenarios. But this is how, or one way we can get this answer. How many different routes could a person follow? Go from A to B if you're always moving closer to B, meaning you're either going upwards or to the right. So again, we can go to our calculator and get our answer for this. 10 factorial divided by, in brackets, 4 factorial times 6 factorial. Gives us an answer of 210. And we're going to see as we finish off this chapter, there's going to be 2 different ways that we, or 2 other ways that we could handle these types of questions. But that's one of them. Okay? How many 3-digit numbers can we make using digits 1, 2, 3, 4, 5? And repetition is not allowed. Okay? So we could do this one a couple different ways. One of them would be using the fundamental counting principle. There are no restrictions. It doesn't have to be even. It doesn't have to be greater than a certain value. You're just arranging 3 of these 5. So you'd have 5 choices for the first digit, then 4, then 3. 5 times 4 is 20, times 3 is 60. So that would be one way to do it. Another way, you could use permutations. 5p3. If you do 5p3 on the calculator, you get the same answer. Right? We said that permutations are another way to do fundamental counting principle as long as there's no repetition. If there is repetition, you can't use permutations. You have to use the fundamental counting principle. Part B, how does the application of the fundamental counting principle in Part A change if repetition is allowed? So when we mark down our 3 spaces, you'd have 5 choices for each one, which is 125. Okay? Evaluate 7p2 using factorial notation. So that's using the formula, 7 factorial over 7 minus 2 factorial, or 7 factorial over 5 factorial. Gives us an answer of 42. And you could check that by going 7p2 on the calculator. Oh, I press C2. Try that again. There we go. Gets our 42 answer. We saw a question similar to question B yesterday. Show that 5 factorial minus 3 factorial is equivalent to 19 times 3 factorial. Show that those two are equivalent. And if you remember, we did this by using common factors. 5 factorial can be written as 5 times 4 times 3 factorial. And the reason I stopped at 3 factorial is because that is the term that's in the second position. So now I can take out a common factor of 3 factorial, and I'd be left with 5 times 4 from the first term minus 1 from the second term. 5 times 4 is 20, take away 1 is 19, and there we go. We've shown that that is equal to 19 times 3 factorial. Okay, so that one is done. Question C says to solve for n if np2 equals 56. And as I said yesterday, you can definitely use your calculator and do some guessing and checking to get the answer, but that could only be used to check your answer. Okay, the expectation would be that you'd have to solve this algebraically, which means that we would use the NPR formula to simplify NP2. And we simplify by expanding, and we always expand the expression that's the larger of the two. N is greater than n minus 2. So n factorial will be n times n minus 1, and we could go on forever, subtracting 1 each time. But we stop at n minus 2 and put a factorial on the end because that's what the denominator is. So the n minus 2 factorials will cancel. That's the whole point of doing that. And we're left with n squared take away n equals 56. Whenever you have a quadratic to solve, we always make it equal to 0 so that we can do what? Yes, the F word in math. We're going to factor. N minus 8, n plus 7. Negative 8 times 7 is negative 56. And negative 8 plus 7 gives you your negative 1. So our solutions would occur where each factor equals 0, which would give us 8 as one answer. And the second factor, n plus 7 equals 0, that gives us negative 7, which is extraneous. Remember, n refers to the number of objects you're choosing from. You cannot choose from a negative number of objects. So the answer should just be 8. And we can check that. Make sure that 8p2 does equal 56. And it does, right? So it checks. How many ways can one French poster, 2 math posters, and 3 science posters be arranged in a row on a wall if the 2 math posters must be together on an end? So there are 6 posters here altogether. So let's start by marking down 6 spaces. And it says that 2 math posters must be together on an end. So that means there's 2 scenarios that we have to look at. They can be on the left end or the right end. They can be at the beginning or they can be at the end. So if the 2 math posters are on the left end, that means there's 2 factorial ways that they can be arranged. Notice it doesn't say that the posters are identical. They're different. So switching them around will give you a different look. It's a different permutation. So it'll be 2 factorial times the remaining 4 posters could be arranged in 4 factorial ways. And if they're on the right side, it's going to be the same thing. 2 factorial ways to arrange those 2 map posters times 4 factorial ways to arrange the remaining. So it's the same expression. So we can just do 2 factorial times 4 factorial times 2. Two factorial times 4 factorial times 2. So it's a total of 96. Because remember, the word or means to add. Part B, what if the 3 science posters must be together? So if we mark down our 6 spaces, the 3 science posters must be together. So remember, when our objects have to stay together, they count as one thing to be arranged. So I've got one object to be arranged, which consists of the 3 science posters together, plus 3 more gives us 4 objects to arrange. That would be 4 factorial. But you also have to multiply by 3 factorial, which would represent the ways that the science posters can be arranged amongst themselves. It doesn't say they have to be in a specific order, so they can be arranged amongst themselves. So 4 factorial times 3 factorial, 144. And then part C, what if the 3 science posters cannot all be together? So I would do this one by taking all possibilities minus the possibilities with science posters together. All possibilities would be 6 factorial. Minus the possibilities with the science posters together, we just calculated that in part B. That's 144. So 6 factorial. Take away 144. Gives us 576. Now, when we did that example with Simone and Caddison and the cat fight, there were only 2 students that had to be separated. So I showed you a different way we could do it, marking down spaces where they could go. But there were only 2 students that have to be separated. In this case, there'd have to be 3 things to separate. You can still do it that way, but you'd actually have to do 2 different scenarios. One of them being all 3 science posters separated, another scenario being 2 of them together, and the third one separated. You can do it that way, it's just much more complicated. Okay, so I would just do it this way. All possibilities minus the ones with the science posters together, much easier than doing it the other way, because you'd have to do, again, the 2 different scenarios. Okay? So we've already talked about this kind of situation. To solve problems, you must count the different arrangements in cases. For example, you might need to determine the number of arrangements of 4 girls and 3 boys in a row of 7 seats if the ends of the rows must be either both female or both male. So we've done questions like this already. If you must have girls on the end, that's case 1. There'd be 4 choices for the first girl, 3 for the second. Okay, there are 5 students remaining, so that's 5 factorial. And if the boys would be on the ends of the rows, there are 3 boys to choose from for the first spot, 2 for the second, and then 5 factorial in the middle. So Sometimes we have to do these different cases or different scenarios. We've already seen a couple examples like that. Right? One of them being when we had a 3-digit even number. What happens if the first digit was even and the first digit was odd? We had to do both those scenarios. And we've seen a couple other examples where you have to do scenarios. So this next one will be the same. How many 4-digit odd numbers can we make using the digits 1 to 7 if the numbers must be less than 6,000, and again, no digits are repeated. Okay, so the two scenarios that we would look at, just like we did before, would be if the first digit is even, or if the first digit is odd. Okay, so 4-digit numbers. If the first digit is even, so that would mean it can either be the 2, the 4, or the 6. However, the digit must be less than 6,000, so it can't be a 6. So that means we only have two possibilities for the first digit. Right? We started with 3 even digits. We've already used one of them up. I'm sorry, 4-digit odd numbers. So there are 4 odd digits to choose from: the 1, the 3, the 5, or the 7. So we started with 7 digits. We've used 2 up. So now we'd have 5 choices for the second and 4 for the last. So you multiply these 4 numbers together. It's 10 times 16, or 160. Now, what if the first digit is odd? That means it can either be a 1, a 3, or a 5. Again, because the number itself must be less than 6,000, that first digit cannot be a 7. And now, instead of having 4 odd digits to choose from, we only have 3, because we already used one for the first position. There's still 5 for digit 2 and 4 for digit 3. Now you're going to multiply 15 times 12. Which is 180. And when you add those together, you'll get 340 as our answer. Yeah, you're right, Dick. Jason, it can't be a 7, but it could be a 5. Okay, so that deals with permutations. We're going to start combinations. We've been saying that permutations are used when order matters. When order doesn't matter, that's where we use combinations. And I gave you a scenario yesterday about choosing students to sit on a committee. Well, if there's going to be a president, a vice president, a treasurer, etc., order matters. But if the students just all sit on the committee and they all kind of share the same role, then order doesn't matter. That's an example of combination. Another example here, if you're addressing an envelope, you need to write the postal code in the correct order. However, if you're talking about how you put it all together, putting the address, putting the postage on there, and putting the contents in, they can be done in any order. That's an example of a combination. So we'll look at questions where order does not matter, and that's what a combination is. A selection of a group of objects taken from a larger group for which the kinds of objects selected is important, but not the order in which they are selected. There are several ways to find the number of possible combinations. Okay, good luck. One is to use reasoning. You can use the fundamental counting principle, but then you'd have to divide by the number of ways that the objects can be arranged among themselves. So that will work. For example, calculate the number of combinations of 3 digits made up from the digits 1, 2, 3, 4, and 5 without repetition. So you'd have 5 choices for the first, times 4 for the second, times 3 for the third, which is 60 ways to arrange 3 items from 5. However, 3 digits can be arranged in 3 factorial ways amongst themselves. So if it's a combination, you take the number of permutations, which is 60, and divide by 3 factorial, and give us an answer of 10. There are always fewer combinations than there are permutations. Okay? So this is one way to deal with combinations. The number of permutations divided by the number of objects that are to be selected. The other thing is to use the NCR formula. And that is on the formula sheet. And if we look at it here, it's very similar to the permutation one, except there's an extra factor on the bottom. Right? If you take off the R factorial, that's the permutation formula for NPR. But NCR has that extra factor of R factorial on the bottom. So a combination is a selection of objects without regard to order. All of the 3-letter combinations of P, Q, and R, P, Q, R, and S are there. Those are the combinations. It has to have a P, a Q, an R, and or an S. There's only 4 combinations, but the number of permutations would be much greater. It would be 4 times 3 times 2. Because now when you switch the order, it's a different arrangement. With combination, changing the order doesn't change what the end result is. Again, there's always more permutations than there are combinations. And you can find the NCR the same spot as NPR. Remember, N is the total number of objects we're selecting from. R is the number of objects that we are selecting. N must be larger to or greater, larger or equal to R. One application of combinations is lottery. To win Lotto 649, you must correctly choose 6 numbers from the numbers 1 to 49. Pete began to wonder how many different combinations there were. You see, the order you pick your numbers doesn't matter. In the end, you end up with the same 6 numbers. So how many combinations would Pete have to create to ensure he had the 6 winning numbers? Well, that would be 49C6. You're choosing 6 from 49, and order doesn't matter. So 49 C6 is 13,983,816. So that is how many different possible combinations of 6 numbers are available if you're selecting from 1 to 49. If you were to buy one ticket with every possible combination and they were $1 each, that's how many millions it would cost you. So you might think, well, what if the jackpot's over this? It's 20 million or 25 million? Why not just go and buy one ticket for every different possible combination? And the problem with that is, what if someone else gets the winning numbers as well? And then you got to split the pot. That wouldn't be good. It was a couple years ago, there used to be a lottery in Michigan called the Roll Down. And so what it did is it kept building. If no one won the jackpot, that money just went back in like it does for our lotteries here. But then after it got to over $1 million, they had a roll down, they called it. And so what it meant is that the lower prizes had a higher payout than they normally would. Well, this retired guy in Michigan started looking at this, and he figured out as long as he bought enough tickets, he was guaranteed to win more money than he'd spend, as long as he would buy enough tickets when that roll down event happened. So he started doing this, and then he brought some of his other friends in to it as well. When it was all said and done, they won over $27 million US until the lottery corporation figured out what was happening and they stopped the roll down. There's actually a movie that just came out, and I think it's on Amazon Prime. It's either that or Netflix, based on this true story. It's called Marge and Jerry Go Large. Yes, Bryan Cranston plays the guy. Absolutely. So originally it was in Michigan, and after the first couple of weeks of doing this, they were winning, and then the Michigan Lottery Corporation, they just canceled the lottery. Not because they got caught on to them, but they just canceled that part of the lottery. So then it went on to, I think, maybe Rhode Island had the same lottery. So these people, every time the roll down happened, they would get in their vehicle and they would drive 9 hours to that state and they would buy all these lottery tickets. And they'd wait for the draw and they would go through them and figure out which ones were winners and cash them in. And $27 million. They weren't doing anything illegal. That's right. The Lottery Corporation set up the rules. So yeah, it's called Marge and Jerry Go Large. You can watch it. I think it's on Amazon Prime. And yeah, Bryan Cranston plays the guy. Example 2. Rihanna is writing a geography exam. The instructions say she must answer a specified number of questions from each section. How many different selections of questions are possible if? First, she must answer 2 of 4 from part A and 3 of 5 from part B. Again, the order that she selects these questions doesn't matter. Doesn't matter if she selects the first question from part A and then does the fourth, or she does the fourth first and then the first. Doesn't matter. This is an example of combinations. So from part A, there are 4 questions. She's going to do 2 of them. That would be 4C2. And, so times 5 questions from part B, and she has to do 3 of them. This is a type of question that's fairly common on the diploma exam. Very straightforward. Okay? Where you have 2 different cases and you're selecting a certain number from each case. 4C2 times 5C3. Gives us a total of 60. So that's how many different ways she can choose to do these questions. Part B says, what if she must answer 2 of the 4 questions in Part A and at least 4 of the 5 questions in Part B? So this is another one of these examples where we have to look at scenarios. The 2 scenarios would be 2 from Part A and 4 from Part B, or the other scenario would be 2 from Part A and 5 from Part B. It says she must answer at least 4 of the 5 questions in Part B. So that means 4 or 5. So these are the 2 scenarios that we have to deal with. And remember, the word and means to multiply. So 2 from Part A would be 4C2, and 4 from Part B would be 5C4. And the other thing I should write here is that, well, yeah, actually I do have it there already, the or's part. And remember, or means to add. So then we go to our second scenario, which is 2 from Part A times all 5 from Part B. And 5C5 is 1. Right? If you're selecting 5 from all 5 and changing the order doesn't matter, there's only one way you can do that. You're going to select them all. 5C5 is 1. But we'll put all these in our calculator. 4C2 times 5C4 whoops, try that again. 4C2. Actually, I should be able to fix that. No, I can't. 4C2. Put the arrow there to get out of that subscript. So that gives us 30. And then 4C2 times 5C5. And like I said, 5C5 is actually 1. So you're multiplying 4C2, which is 6, times 1, that gives you 6. And a total of 36 different ways that can happen. So this next example, again, a common type that shows up on the diploma exam. There are 12 females and 18 males in a grade 12 class. Principal wishes to meet with a group of 5 students to discuss graduation. How many selections are possible? See, they're not filling any specific roles. They're just all sitting on this same committee. So there are 30 kids to choose from, and he wants to choose 5. So it'll be 30C5. So 30C5 is 142,506. So a big number. How many selections are possible if the group consists of 2 females and 3 males? So now we have to break them down between the 2 different genders. From the 12 females, you're going to choose 2. And times from the 18 males, they're going to choose 3. So 12C2 times 18C3. 53,856. So fewer choices than when they were all thrown in together. Part C says, what if one of the females, whose name is Brooklyn, how many 5-member selections consisting of Brooklyn, 1 other female, and the 3 males are possible? So Brooklyn's got to be on there. There's only one way that can happen. We started with 12 females. We've already used 1 of them. We need 1 other, so that would be 11 ways, or 11 choices for the remaining female. And then we're going to have the 3 males, which again is 18C3. So the answer to this one will just be 11 times 18C3. 1 times 11 is 11 times 18C3. $89.76. What about if Jackson, the principal's son, has to be in the group? How many 5-member groups would include Jackson? So again, the remaining 4 can be either male or female. We started with 30 students. We've already chosen 1 of them. Jackson must be there. So the other 4 have to come from the remaining 29 students. And the order they're chosen doesn't matter. So this is 1 times 29C4, or just 29C4. $23,751. Part E says twins, Peter and Sarah, are in the class but cannot both be in the group. How many, that should be 5-member groups, do not include both twins? So I would probably do this one by going all possibilities minus the possibilities with both twins. This is a process that we've used before. So all possibilities would be our answer to part A, 30C5, which was 142,506. Now, what about the number of groups with, whoops, I put that in the wrong spot. Put that back up here. So what about the possibilities with both twins in there? So we wanted 5 people. If both twins are there, now we only have 3 left to choose, and we're going to choose from the remaining 28 students, right? We started with 30 students. If we take the 2 twins out, now we only have 28. And we need to choose 3 from the remaining 28. So 30C5, or we could use the 142,506 that we saw was the answer from above, minus 28C3. Gives us 139,230. Okay? Part F, what if there must be at most 2 girls in the 5-member group? So this is another one we'd have to do in scenarios. At most 2 girls. That means you could have 0 girls, or 1 girl, or 2 girls. So remember, the word or means to add. If we have no girls, that means all of the students are coming from the 18 boys. So that would be 18C5. Or, so we're going to add, what if there's 1 girl on the committee, which means you're going to choose 1 girl from the 12 that are there, and then the remaining 4 have to come from the 18 boys. When we say 1 girl, that means there has to be 4 boys. Or, if there are 2 girls, they'll be selected from the 12 girls that are in the class, but then that means the remaining 3 have to come from the 18 boys. So, let's figure out each of these. 18C5 is 8568. Plus, let me store that into memory. I need to get it back to add it to the other 2. The other one will be 12C1 times 18C4 36,720, which I will store into memory slot B, and then calculate the last part. 12C2 times, times 18C3. Is 53,856. So now we'll go back and add those up. $99,144. Okay. So for practice, this first pages are dealing with permutations with repetition, and the second set of questions are dealing with combinations. There's actually not too many questions there. I would recommend that you try most of them. I will post the solutions to Google Classroom so you can check your answers. Okay?